Welcome to the Crazy Hat Chemist. So another video here on intermolecular forces. So let's get started. Bam! So today we're talking about intermolecular force with a dipole-induced dipole force here. Okay. So an example of this is when an asymmetrical polar water molecule approaches a symmetrical nonpolar iodine molecule. The negative pole of the water molecule approaches the iodine. It could have been the positive one, but I'm giving an example of the negative end. So it could be either end of that polar water molecule. Okay, that polar water molecule temporarily distorts the electron cloud of the iodine molecule. This is an induced dipole, or polarization of the iodine molecule. It's induced by the polar water molecule, that is. Now, with the iodine molecule having a polarization, that is an induced dipole or a temporary charge separation within that molecule, the water molecule and the iodine molecule are attached or attracted to one another. Okay? This allows iodine, a non-polar molecule, to be soluble in water, a strongly polar molecule. Okay, so here's a diagrammatic view of this. Here's that water molecule here. So the red is representing the oxygen, and the whites are representing the two hydrogens on the polar water molecule. There is a dipole moment, and that arrow is representing that dipole moment of that water molecule. There is a symmetrical iodine molecule, and notice that the negative end of that dipole moment of the water molecule is approaching that iodine molecule, and it's spherical. It is non-polar. Okay, now what happens is that this water molecule induces a charge separation within that non-polar molecule of iodine. That is, now the partial negative end, it is pushing the electrons away. That is, with the water is pushing the electrons away within the iodine. Okay, and now there's this temporary charge separation within the iodine molecule. And this happens because iodine has a relatively large molar mass and is a relatively large molecule itself. What will happen then, consequently, is that the iodine molecule that has a charge separation and the polar water molecule will have a dipole-induced dipole interaction here. And that will cause further iodine molecules to have the same charge or charge separation or polarization. So you can see here I have iodinated water here in this container, and there's solid iodine at the bottom here. Okay, and then there's aqueous iodine that has gone into solution here at the top. Super cool. A non-polar molecule will go into water, a very unusual circumstance. And that is due to the fact that water is so very polar, and iodine is very large, has a large electron cloud, a large molar mass, and that polar water molecule can push those electrons around within that iodine molecule, forming that charge separation, allowing iodine and water to interact. That way, that non-polar molecule of iodine will go into solution. Here's a really cool trick though. If you have some iodinated water, and if you have some oil at hand, like mineral oil, something relatively non-toxic, mix iodinated water with mineral oil, and what do you get? You'll extract out the iodine, because the mineral oil is non-polar, and the iodine would rather be in the non-polar solvent of that oil, of that mineral oil, and it will the iodine will be extracted out of that aqueous solution, and then the iodinated mineral oil will be like purple in color. Super cool. Give that a try. I am the Crazy Hat Chemist, and of course I got myself a crazy hat. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and I'm going to see you next time for another video on intermolecular forces. Bam!